So hi, everybody. My name is Margalit. Last year, I tried really hard to scare you out from using atomics ever. Apparently, I really didn't do a good job because I'm still here. So who knows? So if I cannot dissuade you from using atomics, at least please do it safely. So just to recap, because not everybody actually remembers what happened last year for very good reasons. So before we had any atomics, races are actually undefined behavior. So if you access the same memory location from two different threads at the same time, and one of them is a write operation, you get undefined behavior. All bets are off. Your program is completely broken. You can't get any guarantees out of it. And there are very good reasons for this undefined behavior. It's caches, it's optimizations, it's all the good stuff that you don't want to lose. But we still want to have proper concurrency, so this is why we have core atomic that is supposed to give us defined semantics for races between different threads accessing the same location. And by default, we get what is called sequential consistency, which I'm going to give a couple of words on later on. But the syntax in this sadly isn't that amazing, so you're going to use atomic load or atomic store over a variable, and it's easy to get wrong. This is why I prefer the C++ way, and I try to create a class to a struct to mimic it, which is an atomic, and then you can simply access the struct in a very easy manner. Just write a equals 32. A plus equals to 5, and you get A equals 37. And the idea is that you're going to get the default behavior of using the atomics correctly by this. So let's assume we have this. Now, if you're going to use atomics, sequential consistency is your best bet. And this gives you guarantees about how you can reason about your program. Specifically, it means that you can think about a simple interleaving of commands from different threads and not have to reason about funky behavior we're going to see later on. So for example, consider this example that is called store buffer. We have x and y initialized to 0, global variables. And then one thread, the left one, is going to write 1 to x and read the result of y. The thread on the right is going to write 1 to y and read the result of x. So under sequential consistency, a possible execution is going to be such that first we write 1 to x and update our global view of the memory. Then we can read the result, the value of y into a, which is currently 0. Afterwards, consider writing 1 to y, for example, update the memory, and then read the value of x, namely y, from the memory and write it to b. So this is an example of an execution we could have. We could also have run the mirror image of this and end up with a equals to 1 and b equals to 0. Another possible execution that we could have would be writing 1 to x, writing 1 to y, and then reading the values of y and x to find the result of a equals 1, b equals 1. Now, try to convince yourself that under the semantics I just defined, you shouldn't be able to ever get a equals 0, b equals 0. If you somehow manage to figure out how to do this, please come contact me afterwards and we'll figure it out. But this is easier to reason about because just think, okay, this was running, that was running, etc. So these are the possible behaviors we can get out of the program, and we can work with this. Now, sometimes it's not enough. We want to read, modify, write operations so that we can fetch and add something, increment by 1, for example. So x++ isn't equal to just reading x and writing the value plus 1 to the memory. Because otherwise, if it wouldn't have been atomic, then any other thread could have interjected in between reading the value and updating it, and we could get horrible results that we don't normally want. So we have, just like we have fetch and add, we also have exchange to replace the value with something else and read the old value, or the more powerful compare and swap, which compares the value in the memory to something, and only if it matches, atomically swaps it to something else, but otherwise keeps it intact. Very useful. So to recap, if you're going to keep using atomics and you don't want to go crazy, keep it to sequential consistency. You can think about it just in terms of interleaving from the different threads. You'll keep your sanity this way. You get total order over all memory accesses to atomic locations. You'll be fine. There's only one penalty that we're going to pay for this. it's going to force cache flashes all over the place. You're gonna prevent reordering of statements. The compiler won't be able to optimize your code very well, but you'll keep your sanity and your hair. So consider paying this lost performance. It might be worth it. But since I didn't manage to convince you, let's go lower level. So basically in C++11, there was a new memory model introduced in order to accommodate the need of programmers to actually being able to reason about their programs and of the hardware to actually be able to do stuff efficiently. So there was a bunch of weaker accesses, and these accesses were, this type of memory model was adopted to Rust, to LLVM, to D, all over the place. Races are going to be still defined, so that's great. Our program is defined, we can work with it, but we're going to pay less synchronization. Things are going to go horribly wrong if we don't take notice. If you don't know why, go watch the talk from last year. And I should warn you, and I'm going to warn you again later, do not mix the weaker access you are going to see with sequential consistency access to the same memory location. You're in for trouble if you do that. You've been warned. Okay, so if we want explicit access, my wrapper struct has it. We basically have the load store functions fetch and add, and there is a compile time argument defining which type of memory or access we want. And the default is sequential consistency for good reasons. But if you deviate, okay, go for it. So first we'll consider the release acquire fragment. It's easier to reason about than going even lower level. We have total order over the writes for each location by itself, but it's not totally order between different locations. So you have to be more careful. And the good news that's going to make it worthwhile for you, it's free on x86. So you can get the extra performance you want without actually sacrificing too much. So what happens in release acquire is basically that whenever a thread reads from a different location, it's going to synchronize with that location. So for example, in an example called message passing, if the thread is going to write 1 to x and then 1 to y, now the thread on the right is going to read the value for y. If it reads the value of 0, nothing synchronized, we don't know anything about what's going to be in x. But if we do read the value 1, then the value was read from the right of 1 to y on the left thread. So we are guaranteed to know that about this write of 1 to x, that it happened. So we can only read the value of 1 for x. There's an option to think about it in terms of graphs, which I shortly described last year, and I'm not going to enter into the semantics. But there is also another perspective you can consider, just to add something new for people who already watched the talk last year. We can also consider it in terms of messages. So the memory isn't just value 1 is written to x, but value 1 was written to x at some timestamp. So initially, the memory is empty. So it has the initialization messages that x was written to, 0 was written to x, 0 was written to y at timestamp 0. And the view of the threads is basically these are the values for x and y and the timestamp that the thread is aware of. Now, when a thread is going to write the 1 to x, for example, it's going to choose a timestamp that is greater than the timestamp it has and not used in the memory, and use that for the message. So basically, there is a new message that says 1 was written to x at time 2 for x, with timestamp 2 for x and timestamp 0 for y, because this is the current view of the left thread. And when it's going to write 1 to y, it's going to create a new message, and it could choose a new timestamp, for example, 1, because the timestamps for different variables are independent. And the new message is going to say that the timestamp for the variable x was 2. So that if at some point a different thread, the one on the right, is going to read this message, it's going to incorporate these values of time. And it may only choose to read variables that have greater or equal timestamp to what it knows that happened. And now, because of reading this value, the view of the right thread was updated, and now it must know of timestamp 2 for x, so it cannot choose to read the value 0 from the initialization. Now, this looks simple, but it diverges from sequential consistency. Because early on, in the store buffer, we couldn't read the value 0 for both x and y, but now we can. Since when we write 1 to x and read the value of y, do we have any limitation on the timestamp of y at this point? No, we can read from the initialization. Similarly, on the right thread, when we wrote 1 to y, fine, you created a new message, it knows of y, and that's it. So when we read x, we can still read the value 0. So unless we have something that's going to synchronize us, then we can end up with weird behaviors that you probably don't want unless you know what you're trying to do. Another divergence point that you can have is this simple example. Say we write 1 to x and then 1 to y. Okay. And on the other thread, we're going to write 2 to y and read the value of x. Now, under sequential consistency, this looks fine. I mean, I could have written 2 to y first and then read the value 0 for x from the initialization, and only then execute the thread on the left, writing 1 to x and 1 to y. So where does it break? And the answer is that if there is a third thread observing this, we can actually see that the third thread is going to say that 1 was written to y first, and only then 2 was written to y. So at this point, y is equal to 2, but we still somehow managed to read 0 for x from the initialization. So it's a price you have to pay. But with Relix Require, I'm pretty sure you can reason about it to at least a reasonable degree. Now, if we require synchronization, because, I mean, I don't want to be able to read 0 for both of them, for example, then we require the usage of fences. So we have a sequential consistency fence. And every 2 sequential consistency fences are going to be ordered in some direction, one or the other. You don't control it, so it goes either way, unless something forces a very specific way. And sequential consistency fence does not equal cache flush. Do not deceive yourself into thinking that it does. It just means that it's a synchronization point that needs to synchronize with something else. So if you have a single sequential consistency fence in your entire program, it's useless, it's not going to sync with anything, you can just remove it. And if you're going to put a sequential consistency fence between every 2 atomic accesses that you have right now, then you're going to actually restore your sequential consistency. So you can go back if you need, and in order to trigger a fence, you call atomic fence. Great name. Now, this still synchronizes, so we want something even cheaper with even less synchronization. So the cheapest access is called relaxed in the C11 memory model. For some reason that I cannot understand, it was named raw in the D library. Someday it might get fixed. I can only hope. Anyway, it's the cheapest atomic. It should be compiled to the cheapest move command in the hardware, basically, whatever it supports. It provides absolutely no synchronization. It's still monotonic over accesses over writes to allocation. So if I wrote 0 to x, 1 to x, 2 to x in this very specific order, then I'm guaranteed to read them back in this order and not miss something. So if I read it at first 0, I can read the second time 0, 1, or 2. If I read at first 1, I can only read 1 or 2. And if I read 2 at first, then there's only 2 that I can still read. So in terms of the inner, the variable itself, it cannot be ordered in the same thread, but different variables can be reordered and might be reordered. So if we go back to the message passing from earlier, we can see that if at first 1 was written to x, 1 was written to y by the left thread, the right thread may read 1 for y, but it could still read 0 for x, because there was no synchronization. The hardware might as well could have just changed the order of the writes to the variables. The compiler could have done it. Anything could have happened. So you have no guarantees. It's a lot more harder to reason about. It's a lot more harder to work with, but you can get better performance of it if you know what you're doing. SC fences are still there. Their semantics are more complicated because of the different writes that we have and read. And if we need to the explicit version of atomic fence, it basically has a compile time argument defining the type of memory order. And in addition to the sequential consistency fences, we also have release and acquire fences. They're similar to release acquire operations over an atomic location. But, they allow us to synchronize threads, but they're generally stronger than the equivalent operation over an atomic variable because they can affect multiple variables at the same time. So if we were to restore the message passing example from earlier, we would have added a fence release, for example, between the writes to X and Y. By itself, it does nothing. It just means that all writes past the fence release are going to release the information that the thread knew about at the time of the fence. Then, due to some relation that I'm not going to enter the details, if we read this write on the other side, then we might acquire some knowledge at some point in the future if we execute a fence acquire. And at the point of executing the fence acquire, then we actually have this knowledge of what happened, and we can, again, restore the behavior wanted to prevent reading 1 for Y and 0 for X. So we have the fence release, fence acquire, and we also have fence release acquire that does acquire release that does both of them at the same time. So just saving statements. And I'm going to warn you again. Do not, under any circumstances, mix sequential consistency and release acquire relax access to the same memory location. You're just digging your own grave. Please do not do this. There is an example for this that I would prefer to skip. And as soon as you mix them, everything gets even more complicated than it already is, and there's absolutely no reason you should want that, ever. So please be afraid of incorrect usage. OK, so this is just a recap to just make sure everybody is on the same track. So how are we actually going to use this stuff correctly and keep our sanity in the process? So the rest of the talk is heavily based on a paper by Sinclair et al. About chasing away rats that tries to defines usage for relaxed atomics and that are going to be safe and OK and that you shouldn't be able to get wrong. So the first example we have is unpaired atomics. Basically, let's say we're waiting for something to happen. Let's say we have a low activity queue and just try to find out when the queue actually has a job for me to process. So while I wait for the queue to process, I can just busy wait over and trying to read the variable that indicates whether the queue actually has new work for me. But unless the queue has new work for me, I don't want to synchronize, because synchronizing is expensive. So I'm just going to wait until I can actually observe that the queue has something new for me, and only then process a fence acquire. So this should give you all the reads until you actually see this change. They're going to be faster and cheaper. So the idea is on the thread that's going to release the operation, you just write it, fence release, and do write. And on the other side, just busy loop until you actually see it with relaxed access, and only then acquire it with fence. Another example is commutative atomics. These are basically event counters that shouldn't get optimized away, but you don't actually need them to synchronize between threads. So I just want to have 10 threads counting how many jobs they process and know at the end of the execution how many jobs did I process at this point. If I were to use non-atomics, this would be undefined behavior, and I would get incorrect results. So, but since I don't actually need synchronization, I just need to safely count, I can do an atomic fetch and add for the counters in each of the threads. Because it's an atomic operation, I actually will count correctly everything, but they won't synchronize, and I don't care about it. And only later on, when I actually join with them, then I'm going to have then it's going to synchronize with all the threads, and I will be able to read the final correct result. So I'm going to know how many of the values were actually events processed. So this is another pattern that you can use. Another one is non-ordering atomics. When you have different atomic variables that you don't actually need to synchronize and you don't actually care about their order. So for example, if I have a master thread that's going to create some workers to do its work, at some point in the future it's going to decide, yeah, they're done. So it's going to be able to write in a relaxed manner that they should stop, because it's not going to give them any new information other than the fact that they should stop. So there's no synchronization required. And then, after it's going to join them, it's going to check a dirty flag to see if, OK, I need to clean up. If I do need to clean up, then I'm going to do the cleanup. But the idea is that at this point, I can just read the value of the dirty flag and just in a relaxed fashion, since I already joined the workers. So I'm going to know what are the changes they've done in the process. The workers, on their end, are going to read the stop flag each time. Again, they don't require any synchronization. And if they find out they should stop, then they're going to exit and finish their execution. Now, during the execution, if some condition was met and we are going to require a cleanup, they can just update the dirty flag with a relaxed fashion that the cleanup is required. And again, they don't require to tell anything to any other thread. If multiple threads are going to set the dirty flag, we don't care. Writing true over true is still true, so we're still going to require the cleanup. And the idea is we are able to pass this bit of information without actually caring about synchronizing anything else. And if the compiler can figure out how to do it better, go for it. We don't care. Next pattern is split counter. Say, for example, we have multiple threads that are going to be doing some process of computation, and we have some GUI threads that want to know to make a nice percentage bar showing the progress, for example. So it's perfectly fine if the progress bar is going to be a bit out of date and not entirely correct, as long as it's going to monotonically increase, because we don't want the progress to jump back and forth. And then each of the threads can just process its own counter in a relaxed fashion and update it. It won't trigger synchronization that we don't care about. And the GUI threads could just go for all the threads, read their values. And it might read stale values, we don't care. But because we have, again, multiple accesses to the same memory location for a given thread, we are going to be guaranteed that we're not going to see a lower value that we've seen in the past. So we're only going to actually see the progress. So again, this is a safe pattern that allows us to use relaxed access without synchronization in a very contained manner that we can reason about. OK. All of the examples until now are fairly simple. This is where things start to get a little bit more complicated, because we actually had to cheat to simplify things. Let's say we have reference counting. Reference counting also could use relaxed, but only in very specific case of read-only data. Because if you have writable data, then you're going to start to have to actually worry about synchronizing the changes that were done by each thread. And we also cheat our way here because we don't want to worry about things about ending execution before another thread started to even work. So let's say we have capital X, capital Y objects that are going to be reference counted read-only data. And they have a matching lowercase x, lowercase y, indicating how many references we have to this variable. So at first, we initialize them with 2. Basically, we have 2 threads accessing them. And just to simplify things, we have a barrier to make sure that it couldn't be that one thread finished execution before the other started, which would really complicate the example if we want to get it correct. Now, since this is read-only data, we actually don't require synchronization. So when at some point the left thread is going to finish executing and using this data, it could just decrement atomically the amount of instances that we have of usage of this data. And if the value after the deduction is 0, then it means we have no more references. So we can actually mark it for deletion and allow us to delete it. And then when we're done with y, in a similar fashion, we're going to decrement it. And if it's equal to 0, this means this was the last decrement. Since it's done atomically, we can mark it for deletion. And the other thread on the right is going to do exactly the same thing, just in the reverse manner. And we only care about basically if the value reached 0. And we can freely do it with as many threads as we want. And because it's read-only data, no synchronization was required. Which brings us to another example, fairly simple. when we don't actually care about the data as long as it's going to be unique. Like when you're trying to get IDs for stuff. We can just, if you had give me random value that didn't happen in the past, you can just use fetch and add. And it's going to increment some counter. The counter is going to give you a new ID. The ID didn't happen in the past. You can use it. So, but you don't require any synchronization, just like you wouldn't get any synchronization from the random function. So again, we can use fetch and add with relaxed, and this should be fairly safe. Again, you didn't require synchronization, you didn't ask for synchronization. The last example is access for speculative atomics. Seqlock is a fine example. Basically, the idea is we're going to speculatively load values, assume everything is going to be fine. And if for some reason they don't end up being that, okay, fine. We can just discard these old results. We don't need them. We can try again. So we'll go slower over this one. We have a sequence number that is going to wrap our Seqlock. When we're going to write values, we're going to write basically to many variables, x1 to xn. For space constraints, I only have 2 variables. And then we're going to update the sequence number. The sequence number is going to be an odd number to indicate a store is in access, taking place. And we are going to initiate a fence release. This means that if we end up reading anything past this point by a different thread, then we are going to make sure that if we actually post and acquire, which we will, we are guaranteed to read the odd sequence number. So we are going to know that this was actually taking a value that was read mid-transaction. If it was read mid-transaction, it means it's actually a bad read, and we should discard this result. We can then proceed to writing all the values that we care about in relaxed fashion. They're all going to actually release the old sequence number due to the fence release. And once we're done, we can update the sequence number in a release write, indicating the new even number, which would then mean that if we read a new even number, we are going to be guaranteed to read at least the values that we wrote in the last Seqlock writing iteration. And if we read something else, then we'll end up with, again, with a different sequence number later on. The read on the other side is going to read the sequence number in a relaxed fashion. If it's odd, that means that some transaction is taking place right now, and we should just try again and again until we find an even number, indicating a transaction is actually finished. Once it's done, we can fence acquire. Again, this is the same pattern that we've seen earlier here, just trying to read in a relaxed fashion until some event takes place that we know that it can actually should synchronize, and only then process the fence acquire instead of doing it on every single iteration of the loop. Once we synchronized, we can try to read all the variables protected by the sequence lock and process a fence acquire after all of this is done. This is faster than simply using release and acquire because it allows the variables protected by the Seqlock to be reordered for better memory access. And once we've done this acquire, we actually know that if we are going to read the sequence number again, if it's going to be the exact same value, this means that we actually managed to read an entire transaction, we can use the values. But if we ended up reading something newer, then because of the fence acquire on the right would synchronize with the fence release on the left, we are actually going to find a different odd or even whatever sequence number that's going to be different from the one we expected. So it means something changed while we were reading, so we should reset everything, try again. But if we do manage to reach the same sequence number, then everything's great. We can actually use these values, and again, we actually read something with less synchronization than we required. Yeah, thank you.
And I've walked all the way down from the back, and I haven't seen a single hand come up. Come on, questions.
I'll give you the answer. Don't use atomics. If you do use atomics, use quotient consistency. This is the answer.
And this is something I've been wondering a bit. When we're talking about all these standards of synchronization that you can apply when doing atomic operations, To what extent is, just as an interest, to what extent is this a matter of someone thinking up a specification and then writing a CPU for it, or to the extent that this is, for instance, relaxed consistency corresponds to a specific piece of hardware in the CPU that's doing synchronization in a specific way?
That's a great question. And the answer is that some of it was defined by trying to get the programmers to be able to reason about the program. Some of it was trying to actually capture semantics of the hardware. So, for example, the relaxed access were tried to match to the lowest, cheapest access one could get from the hardware. But it's hard to work with. On the other hand, because of the really square semantics that are free on the, as long as you don't have atomic fetch and add and stuff like that, they're free on x86. So again, it was tried to be captured in a nice manner. And ARM later on introduced actually new assembly in newer hardware that is actually able to provide this really square access. So it goes both ways.
I'm completely aligned with your position, right, or your admonition to not use them. But I'm wondering, what are the use cases, actually where there's been benchmarking and so on, where these more lower level primitives are in fact demonstrably important? Right? I mean, they're not. It's not in my universe of things that I'm using. I'm just wondering, can you give us some examples where these lower level primitives or lower level forms are actually demonstrably important in terms of performance?
Okay, so what happens is when you have a lot of threads, and 80 might as well be enough, trying to access the same memory location, and then you're starting to have cache coherence protocols fighting over the location, especially if they all try to write, and you actually end up trying to get, in order to get cache coherence, you get everything slower. So you try to minimize the amount of time and the amount of synchronization you try to have over a single variable. On x86, for example, you could end up doing cache flushes all the time because this is how you actually make sure that the buffers are updated in the memory, so you'll always be able to read the last location, the last write location.
Yes, I understand the. I understand the theory. Oh. I'm just wondering if there are actually workloads, maybe microservices, or I don't know, something where this is actually demonstrated. I very clearly understand the hardware architecture. Yeah.
As far as I'm aware, there are work stealing queues that actually have demonstrable difference between the execution if you use locks or atomics, or going even lower level with the atomics.
All right, we have a online question here from Ricky. Since shared requires atomic usage, would it not be better if this was part of the language rather than library and the defaults be best naively?
Yes. Obviously, yes.
So in the event counter, right, you have multiple threads. You're doing relaxed.
This one or the other one? You wanted this one, I think.
No, this one. Oh, no, this one makes sense, I think.
Okay.
I think.
Okay, we can walk over to both of them. So which you prefer first?
No, there was one with the event counter in the title somewhere.
Oh, this one that has
yeah.
event counter that doesn't get optimized away.
So I didn't quite get this
okay,
diagram.
So the idea is I just want to know how many times something happened, how many events took place, and I don't actually need threads to synchronize between them. Now, if I would have done x++ in non-atomic fashion, then I'm going to have undefined behavior because it could unroll to multiple writes that first loads to some register the value of the memory, and then some other thread could actually load the values, increment, etc. But the first thread is going to keep the old stale value and then overwrite it with +1, making me lose all the progress that was done by other threads in the meantime, for example.
Yeah.
So I have to use an atomic operation. But I don't need to synchronize with new threads. I just want to know how many events took place.
These axes, they're global, right?
Yeah, the axes are global, but my axis is going to be relaxed because I don't need any synchronization here. And they're going to synchronize once I do a join with the main thread.
Okay. I don't understand what they do need to synchronize.
They don't. I just care about actually counting correctly here. And for counting correctly, a single fetch and add operation is enough without any synchronization.
Okay. Well, let's talk later.
Okay.
Yeah, that sounds like a beer conversation. Yeah, I think we're good for questions. So thanks again.